All right, let's take a look at another exercise involving combining conservation laws together. So we have this block up here that is released from rest at the top of this hemispherical bowl. So it has this height of r that it falls down, the radius of the bowl, and then it slides down. It smashes into this one. The two of them stick together, and then they go up over here. And we want to know how high does it travel up here? What is this new height? So we look at this and we know, if this is actually says it's a frictionless bowl as well. So we can look at conservation of energy from here to here. So energy would be conserved because it's frictionless here. And I guess I could use, like kinematics and whatnot, but it's on this curved surface, so energy analysis will be much, much easier. And so we can use energy analysis down to here, but then during this collision, energy is not conserved, right? Especially in an elastic collision like this. And so during this collision, we'll need to use momentum analysis, and then once they're stuck together and it moves up to here, we'll need to use conservation of energy again. So this will be the general method. So to set this up, to establish our method more clearly here, let's start out with identifying some points. So we'll call point 1 will be up here when this block is at rest. Maybe I'll call this is block A and this is block B. So they're both at rest actually at point 1. And at point 2, we'll say block A is all the way down at the bottom, just about to smash into block B, but they haven't actually collided yet. So A will be, basically A is in the position where B is, but they haven't actually hit yet. Because think of these blocks as being infinitely small. And then I can call point 3 will be immediately after the collision. When now at point 3, A and B are stuck together, and then at 4 they're stuck together and they're up over here. So this would be point 4 when there's something like this. And we can say from 1 to 2 we'll use conservation of mechanical energy. And then from 2 to 3 we'll use conservation of linear momentum. And then from 3 to 4 we'll use conservation of mechanical energy again. Okay, so let's go ahead and write this out here. So from 1 to 2, knowing that it starts out at rest, so v1 is equal to 0, we can first find out what the speed here is at 2, the speed of A at point 2, and then momentum, etc. So let's start out 1 to 2. We have here actually both of these blocks are mass m. They two identical masses, so they have the same mass. Call them both mass A is equal to mass B is just equal to m. But maybe I'll write it out as mass A and mass B just to kind of get the just for clarity of the solution here at first. So we'll have at point 1 we have just gravitational potential energy, ma g times the height, as we discussed. This would be equal to the radius, right? So magr is equal to the kinetic energy at the bottom, and this is going to be 1/2 ma v, call it v2 squared, right? And plus we actually have 1/2 mass of b, but b is not moving, so that's times 0 squared, right? So this is gone. And so we can get the mass of A cancels out here, and we have the speed at 2, and this is just the speed of block A at 2. This is equal to the square root of 2gr, or 2gh, as we've seen many times before, but h is equal to r here. And then with from 2 to 3 we use conservation of momentum. So we have here The momentum at state 2 is equal to the momentum in 3. So this is before collision, this is after the collision. So the momentum before the collision was just the momentum of block A, since block B was not moving. And so this is going to be mass of A times V2 is equal to the momentum after is the total mass, mass A, plus mass B times their combined velocity, which we'll call V3, right? Since they're stuck together now. And so we can say here, since mass A and mass B are equal to M, I can just rewrite all of these as M's. So this is M, this is M, this is M. And we have here M V2 is equal to 2M V3, right? Or V3 is equal to 1/2 of V2, which makes sense actually. That if I have two masses colliding, one wasn't moving, one was, and they're equal masses, their speed after collision is just going to be half the speed of that one before, which is what this says, and that makes sense. So this is now the speed of both of them right after the collision, right? V3 is the speed of both mass A and mass B immediately after the collision. And then after the collision, we don't have an isolated system anymore from 3 to 4 because gravity acts on it, right? Gravity would be pulling down some net external force. But we can use conservation of mechanical energy from 3 to 4. So then we'll go back, and from 3 to 4, we'll use conservation of mechanical energy. And so we say here, now it was moving, right? It's moving at state 3. It's going to be at rest at state 4. So we have here 1/2 of the mass now is, well, I'll write it as mass A plus mass B times V3 squared is equal to mgh, but m is mass A plus mass B times g times, call it height 4. That's what this is here, h4. And the mass cancels out, it's the total mass, right? And we have here height 4 is equal to V3 squared over 2g. And of course let's write out what V3 is. So V3 was 1/2 V2, so this is equal to 1/2 of V2 squared over 2g. So height 4 is equal to 1/4 of V2 squared over 2g. But V2 was square root of 2gr. So this means that V2 squared is just equal to 2gr. So I can plug that in. So this is 2gr. And we see here that when we do this, that 2 cancels, that g cancels, and we're just left with height 4 is equal to 1/4 r. Which you might have thought originally, like, oh, now I have twice the mass, so it'll only go to half the height. But what happened, the reason it only goes to 1/4 of the height, because remember the original height was r, the reason it only goes to 1/4 of it is because some of that energy was lost during the collision. So 1/4 of the energy. And that's another combining conservation law problem.